Good morning, good afternoon, good evening. So yes, we have been looking at the topic of calculus, and as said before, there's two parts from it. So we probably did the differentiation, and we're going to be moving on to integration. So whether this is a specific lecture for yourselves, it doesn't matter. What I'm focusing on here is integration. So this part here, I can just move through it. If you want to go back and look at it, you can do it. I want to get to the important part for us here. And this is one thing we will be doing, evaluating areas between curves. And that one there, that one's pretty tricky. That'll be all your workings, and we'll come to that, but don't you worry, or that'll be something similar to it. Right. So let's just move on, and like I'm saying here, we actually did do this. We looked at differentiation first. That's fine, but you know what? Because I've looked at integration, and we're going to look at that now. We're going to look at something called indefinite integration. Indefinite integration just means you don't end up with a fixed number at the end. You end up with an expression. So what we're going to do here is, if we have information about the gradient function, the derivative, what we can do is go back and recover the original function. So here we go. Let's just go back to it. Okay. If we had some kind of derived function, a derivative, a gradient function, which was 6x, it could have come from something like 3x squared plus 1, because when you differentiate that, using your rules available, the 2 comes down to multiply the 3 to get 6, 6x, and then subtract 1 from the original power. The 1, when I differentiate a constant, its value 0, so you'd end up with 6x. Also, it could have come from that one, or it could have come from that one. So the derivative for each of them is the same. So like we're saying, in here, we can just generalize here. We just come up with a fixed expression. The value of c is just a fixed number here, a constant. I don't think we're going to go and pin down c in this unit here, but later on you might have to, but you'll have other information that will let you pin that down. Okay, nearly there, let's go for it. Notation. Okay, what we've got here, some people call that the integral sign. That's like a big stretched out S sign. Okay, so that is just going to be part of your instructions. You're going to integrate some function of x. That can be like sine x, x squared, 2x plus 5, e to the 9x. And we're going to integrate that in relation to x. That's what the dx means. So integrate in relation with respect to x, whatever's between them. So they're like bookends here. So that's what we're going to integrate. You're going to have a list of them. And as with differentiation, we just apply the rule to it here. So I'm just going to give you a set of rules. I'm going to go through them one at a time. And like it's saying, f of x is some function of x. F of x is just the same as y. If we're comparing y with x, that is. So, like it's saying here, there's different rules for different functions. Somebody's made these up for you. Somebody's done the hard work. So we'll be looking at things like ax to the n, 5x cubed. What we've got here is a constant over a linear function or a rational function, whatever you want to call it. Trig functions, natural exponential functions, and another type of polynomial where the stuff in the bracket is always a linear function. It's a little bit different from the 5x cubed, the ax to the n, but we've seen these before. Okay, so I'm just going to go through them one at a time. You have got your formula sheet, so I'm not going to bring it up. You can have a look at it. So ax to the n, okay, we're going to integrate that. So that's where we bring on board the symbols. So the extended s sign with the dx at the end, because that's letting you know the variable is x in here. Okay, so according to the rule, what happens is we add 1 to the power, and then we divide by the new power. That is it. You're just moving things about and simplifying. Don't forget, there could be an additional number at the end, plus or minus. We just refer to it as c. So that there is just a constant, it's a number. At this point, we don't know the value of it. Later on, we might have information about it. That is our rule. Okay, let's get an example here. 5x to the power 2. Let's apply the rule. Okay, increase the power by 1, divide by the new power. Okay, 2 goes up to a 3, and divide by the 3. Okay, don't forget about the plus c. Have a look at the number on top, number on bottom, the 5 and the 3. 5 divided by 3. That's not nice. That's for final answer. Okay, that's it. Next one. Number on its own. Doesn't have an x. That's fine. But what we're going to do is give it an x. And we'll do that with a little bit of manipulation here. 3 is the same as 3 times 1. 1 is the same as x to the 0. Put that in. That looks like ax to the n. Okay, apply the rule. Increase the power by 1, divide by the new power. Done. Power of 1, we don't need to see it. Okay, we can just leave it with the x. 3 divided by 1 is just 3, so just end up with 3x. And don't forget the plus c. In future, all you're going to do, number on its own, all you do is just stick an x to it, or whatever the variable is. If it's dt, you would put t onto it, but it's dx up the top line. Just stick x in it. Okay. Similar, integrating a number on its own, -4, that just goes straight to -4x plus c. Done. In this little video, I am not hanging about because, as I keep saying, you can freeze this stuff and go back. Pause it, that is. Okay, let's move on. Okay, we've got 4 terms here. They all look as if they're of the form ax to the n. Let's apply the rule here. Okay, first one, ax cubed. Add 1 to the power, divide by the new power. Let's move on. 4x squared, add 1 to the power, divide by the new power. Next one, 6x, that's really 6x to the 1, add 1 to the power, divide by the new power. -2, number on its own, stick x to it. That's it. Don't forget the plus c. Okay, let's go through each of these and see if we can simplify them. 8 over 4 x to the 4, that's just 2x to the 4. 4 over 3, leave it. Okay, it will give you a decimal that's gone forever, just leave it. 6 over 2x squared, that's 3x squared, fine. Everything else is okay. That's us done. Right. Here, what we've got is we've got a number on the top and the x down the bottom. I don't want x on the bottom with our sets of rules. We need to bring it up the top. Using our laws of indices here, the power has to change sign. So it goes from positive 3 to negative 3. Okay, that now looks like a number times x to a power. We can apply the rule, increase the power by 1 and divide by the new power. Okay, let's tidy this up here. 4 divided by negative 2, plus c. 4 divided by negative 2 is negative 2, x to the negative 2 plus c. That answer's fine. If you were to look up the back of a textbook or an exercise, the answer might not look like that because they don't like negative powers. So what they might do is take the x with a negative power, create a fraction, take it downstairs, and then we've got a negative on the top and effectively a positive on the bottom. Just bring that negative sign out the front. Okay. And that would be fine there. Okay. But what I'm saying here, both of these answers are acceptable. Usually we introduce positive powers because in the olden days it was easier to calculate powers that were positive. Because 5 to the power 2 is a lot easier than figuring out 5 to the negative 2 in your head, that is. We used to do things like that. Okay. We're now going to speak about definite integration. Previously, indefinite integration meant we just had an expression, okay, in terms of x or whatever the variable is, and a plus c. So, definite integration, what's going to happen here is we're going to get a number for the answer, a definite numerical solution, as it's saying here. Okay, everything looks the same, apart from we've got two numbers, top and bottom of the integration symbol, the extended S symbol here. So these are known as the limits of integration. So what's going to happen here? Just apply the rule as per normal, but I'm just going to give you a little kind of graphical analogy here. This is what this could represent. This is like looking at the area under y equals x cubed, and above the x-axis, won't explain that yet, from x equals 2 to x equals 3, these are vertical lines. So that's the scenario we've got there. So, just apply the rule, increase the power by 1, divide by the new power. We don't have a plus c here. What we're going to do here, I'm just going to box it up. I'm going to move my limits to the right hand side. No obvious reason for that. It's just what we do. Take whatever's in the rectangular bracket here and copy it. Okay, I'm just removing x because I'm going to insert a number in here. So put it down once. I'm going to put it down again. And between it, I'm going to subtract. We're now going to evaluate here with my limits of integration. The one on the left takes the upper limit. The one on the right takes the lower limit. Okay. We can now evaluate here, but I might just go back. See the first one, the one on the left, the 3 to the 4 to the power 4, that's actually the area under the curve and above the x-axis from 0 to 3. That's what that is. The second one, the 2 to the 4 over 4, that's actually 0 to 2 under the curve. So I have got two areas here, but the area I require is actually from 2 to 3. So that's why I'm subtracting. So I'm taking the larger area, subtracting the smaller area, and that gives me the desired area. We don't need graphs, okay, but it's just a little analogy there. So here, 3 to the 4 over 4, 2 to the 4 over 4, 81 over 4, 16 over 4. So 81 take away 16 over the common denominator. That's fine. So 65 over 4, if you want to decimalise that, 16.25. That is fine. The context here was area, so I could have put in units squared, but I haven't done so. Don't worry about it. Okay. Different function, new rule. On your formula sheet, you'll see something like that. What happens here, when we integrate, apply the rule, add 1 to the power, divide by the new power, but also whatever number in the brackets next to x, the coefficient of x, it's actually the derivative of ax plus b. Anyway, we just bring that downstairs, it'll multiply that new power, the n plus 1. Don't forget the plus c, so that's your next rule. Okay, example of that there. So 7x taken with 2, that's like your ax plus b. So increase the power by 1, the 3 goes up to a 4. Divide by the new power, but also bring down the coefficient of x at the derivative of 7x taken with 2, which is 7. Don't forget your plus c, but then tidy up the bottom, the 7 times 4, that's just 28. That is us done. Okay, square root of 6x plus 1. We don't like square roots, we need numbers here. So bracket that up, you know that the square root is a power of a half. So we've made an exchange here. Now follow the rule, because we have a rule for this. Increase the power by 1, so a half. When we add 1, it's 3 over 2. Let your calculator do the work. Divide by the new power, and also divide by the coefficient of x in the bracket, which is 6, which is technically the derivative of 6x plus 1. Don't forget your plus c, but then tidy up the bottom. 6 times 3 over 2 should be 9 with the plus c at the end. That's us done. Okay, ax plus b. I keep on saying plus, it could be a minus, it doesn't matter. Plus a b means b can be positive or negative. Okay, this is definite integration because we've got limits of 2 and 3, top and bottom of the integral sign, the extended s. Let's just use the rule first of all. Increase the power by 1, divide by the new power, and also the coefficient of x, the number in front of x. Bring it down. Okay, that's fine. So we're just going to, we've integrated, I've followed the rules, bracket it up, take the limits there to the right, sort out the bottom, the 2 times 6 to get 12. Okay, copy and paste what's in the rectangular bracket on 2 occasions. I've just removed x. Remember, we're always subtracting between these. Upper limit goes into the left hand one, lower limit, the 2 goes into the right hand one. That's fine. I'm looking at the brackets on the top here. Both of these, I think I can do 2 times 3 is 6, take away 1 is 5. 2 times 2 is 4, take away 1 is 3. I'm going to simplify them both. Get 5 to the 6 over 12, take away 3 to the 6 over 12. Okay, 5 to the 6. That's a calculator effort here. 5 to the 6, what's that? 6 to 5. 3, 1, 2, 5, 15, 6, 2, 5 or something like that. Over 12, yep, and 3 to 6, that's easier, that's 7 to 9. 15, 6 to 5, take away 7 to 9. I put them both over 12 because the residual fractions had the same denominator, bottom part. Take that to there. Your calculator would probably simplify that further to there. You can leave that answer like that if you want, or you might want to decimalise it. Just depends what we need the answer for. So that's 1241.3333. That's fine. You round it to however many decimal places you want. That's fine. Leave it as a fraction if you want. Okay, talking about trig here, trigonometry, let's just go for a rule. Doesn't matter where the rule came from, you just want to implement it. So here, sine goes to negative 1 over a cos ax plus b and plus c. That's the rule. Okay, you just want to apply it. Check your formula sheet, should look like that. Or sometimes what some people like to do is absorb the 1 up into the cosine part and the fractional part divided by a. They might put it under it. Personally, I don't like that, but some of you might do, because it's not about me, it's about you, apparently. Okay, so either or. Right, let's go for this one. Sine, you've got your rule, check your rule. I'm going to integrate this here, goes to negative 1 over 2. Sine goes to cos, and bring back the bracket with the contents. Don't forget the plus c here. That's it, done. Okay, this time we've actually got a number at the front. Don't worry, that number will just come down and it'll go on top of the fractional part. Okay, so it'll become negative 15 over the x number 5. Sine goes to cos, bring the bracket down, and don't forget your plus c, but I think we can tidy up the 15 over 5 there. So that will just become negative 3 cos the bracket plus c. Okay, that looks fine to me. Let's move on. Done the sine, done the cosine. Okay, the rule here is cosine when you integrate it, it's 1 over the x number. We're calling a in this case. Cos goes to sine. Bring back the bracket and don't forget your plus c. That's the rule. Okay, and some people like to take the a downstairs. It's up to yourself. That's my preference. Okay. In this one, it's just basic cos x. But we've got limits here. Pi over 3, upper limit, pi over 6, and lower limit. Look at your formula sheet. Cos x just goes to sin x when we integrate that. But just remember, because this is a definite integration question, we need to be using radian measure. Okay. With this one, you could convert these angles. Well, they're not necessarily angles actually. This might be in terms of time or whatever, but we pretend they're angles. In your calculator, you need to use your angle mode. So here, but radians, calculus and trigonometry, it's best to use radians. Okay, so anyway, that is old-fashioned calculator. So ask your lecturer or your friend if you have one, and they'll get into radian mode. Okay, let's integrate cos x to get sin x. Okay, let's definite integration here. Let's box it up, move my limits here. Okay, let's copy and paste sin x, but it'll be just sin with an empty bracket. Another one, and remember you're subtracting. Let's put the upper limit in the left one, lower limit in the right one, and then it's calculator time. Okay. Your calculator might give you an exact answer of root 3 minus 1, and the whole thing would be divided by 2, and that would be 1.732 take away 1, which is 0.732 divided by 2, which is 0.366. Right, so you just round it to whatever you think. If you had been in the class, we'd have sorted that out, making sure our calculators were on radian mode. So if you want a decimal answer, that's fine. If you want an exact answer, it would be root 3 take away 1, the whole thing divided by 2, or root 3 over 2 take away 1 over 2. Whatever, doesn't matter. Don't have nightmares about this. Okay, let's move on. Why don't you try that one? Pause it, try it. Did you pause it? Did you try it? Okay, let's go for it. Sine ax plus b, negative 1 over a, negative 1 over 3. Sine goes to cos 3x plus 1. We don't have a plus c because we've got limits here. And you'd end up with c minus c anyway. Okay, so put my limits on the right for no obvious reason. But anyway, so I'm going to copy and paste the thing in the rectangular bracket. But what I'm going to do is if we just bring it back here. Oh yeah, if you want to put it like that, it's fine. But that's what I like. So I can't show you every single way. I'll show you my way. So what I'm going to do here is, I know I should be copying what's in there, but there's a lot going on here. What I do is, with sines or cosines, if there's a number at the front, I actually factorise that out. So what it means is I only copy the thing in the rectangular bracket, and I'll keep that negative third to the end. Okay, so that's what I'm doing. I'm just factoring out that negative third, or whatever the number is if we have one. So here we go. Like I'm saying, the negative third is out the front, so it's only the cos part. It'll be the cos minus cos. Cos minus cos. Yep. Okay. And don't worry if you've seen something come up on the screen there. I may have skipped a few pages. Upper limit goes in there. Lower limit goes to the right. On the left, I think I can sort that. 3 times 1 plus 1 is 4. I'm going to sort that. If 3 times 0 is 0 plus 1 is 1. I'm going to sort these out. So I've got cos 4, take away cos 1, and I'll have the negative third at the front. Okay, so I've sorted that. Calculator time, don't forget it's negative a third times what's in the bracket, the large bracket. You put that in the bracket, it's not going to give you a nice answer, it will give you a decimal answer. You round it to however many decimal places you want, and when I rounded it, that's what I got. Maybe it was 0.3979 or something. You make a grown-up decision, okay? As long as you're getting that kind of answer, that's fine. Okay, let's move on. Natural exponential function, rule for this here is 1 over a times the original function plus c. That is it. This is a nice one. I like this one. Very straightforward. Or some people like to take the a downstairs. That's fine. Right. Also, some formula sheets of notes are different, but both of these are the same. Both of these are the same. Right. So there, if that's the case, if they're using the EXP, don't get that confused with a button on your calculator. They are not the same. Okay, so that would be another rule which is similar. And if they want to take the A downstairs, that would be acceptable as well. Okay. Right. Okay. This one here, e to the 5x take away 2. What's going to happen here? I'm going to make a fraction, so we'll integrate that. It'll be 1 over the x number, 1 over 5. Okay, I think I went ahead of the game here. And then just times it by the original exponential function upstairs, plus c. That's you. If you want to make 1 divided by 5 0.2, fine. You go ahead with that. Right, here, this time I've got a number in front. of the exponential, I've got an 8. So instead of 1 over 3, it'll be 8 over 3. So that 8 just comes along for the ride. 8 over 3, then times the original exponential, the e to the 3x minus 1. Doesn't always have to be in a bracket. Sometimes we just like to protect it. And let's have a plus c, because it's an indefinite integral. We don't have numbers top and bottom. That's it, folks. 8 divided by 3, there's no point decimalising it here, because we're not going to get a numerical answer anyway. Let's move on. And some people slide 3 underneath the exponential part. That's fine. Okay, we've got a definite integral here. So it's e to the ax plus b. B is 0, so there's nothing after the 3x. That's fine. So we know the 3 is going to get involved. So when we integrate that, it's going to be 1 over 3. Bring back the original exponential function. Let's bracket this up, because we have limits here, 2 and 1, top and bottom. So am I going to take out the third? Don't know. I am. That's fine. Just saves me a bit of time and effort, calculator effort. So only thing I'm going to copy here is what's in the rectangular bracket, the e to the 3x. So there you go. Cut and paste. E to the 3 something. I've removed x. Remember, you're subtracting between them. Let's put in the upper limit on the left, lower limit on the right. So the 2 and the 1. If you think that you can, that those powers of e, you can 3 2s are 6, 3 1s are 3. If you want to sort them out, do so. That's fine. So at this point here, e to the 6 is a big number, e to the 3 is a big number as well. We're going to get decimals here regardless. So that's what I got when I put it in the calculator. Okay, so just you take your time. So you could work out the contents of the bracket, e to the 6 take away e to the 3, get an answer, then divide by 3 or multiply by a third. It's the same. You're going to have something like that there. That's our final answer there. Okay. I think this could be our final little rule here. Let's go for it. So 1 over a linear or a rational function. Thing is about the denominator, the power of x is 1 here. If it was x to the 2, we'd have a different rule, but not at this level. So according to the rule here, for whatever reason, it becomes 1 over a natural logarithm of ax plus b, which was the denominator. Don't forget your plus c, and that's another rule for us. We're just following the rules, okay, and tidying up. Okay. And just in case you don't like the 1 over 8, you can always slip that 8 down the stairs, just like that there. Up to yourself. You are in charge of your own destiny, as long as you can work your calculator. Okay, let's go for a little example. Looks like that there. 1 over ax plus b. I keep saying it can be plus or minus. It doesn't matter. B is a constant, okay, which can be positive, negative, or 0. So, according to the rule, it's going to be 1 over the x number, which is actually the derivative of 2x to give us 7. But we don't really need to know that. We can just follow the rule. Natural log, contents of the denominator, okay, plus c. 1 over 2, just leave it. Don't need to make that 0.5. Or you might want to put the 2 underneath the ln part. Doesn't matter. I'm leaving it like that. That's my preference. Okay. Here, this one's a little bit different. and that we've got a number other than 1 at the top, that number just comes along for the ride. So instead of having it as 1 over 9, it'll be 4 over 9. Okay? ln contents of the denominator in a bracket, 9x plus 2, and don't forget the c part. There's no point doing 4 divided by 9. What's 4 divided by 9? Oh, 0.44444444444. Leave it. Don't touch it. That's fine. That's our answer. Right. Here, oh, looks as if we're doing a third one. The reason we're doing this one is because the x value on the bottom here, the number in front of x is negative. Watch out for that. So here it's going to be 8 over the x coefficient, which is negative 2, ln, and the stuff in the bottom of the fraction, put it in a bracket, 3 take away 2x plus c, but 8 divided by negative 2 is negative 4. So that's why I'm sorting that out there. I didn't leave it like that, even though I'd underlined it there. Try to catch out there. Negative 4 plus c. Done. Okay. Let's go for a definite integration one here. So we've got a 5. So the 5 is going to be in the top of the fraction. It's going to be the 5 over the 2. ln, the denominator in a bracket. So the 2x minus 1 is going to be in a bracket. We don't need a plus c because it's a definite integration. So we're going to box this up. Limits form 3. Make sure they're obvious. Okay. So am I going to take out the 5 over 2? I think I am. Okay. Saves you a little bit of work. You can put that as 2.5 if you want, because of the exact decimal representation of the 5 over 2. So we're going to cut and paste whatever's in the rectangular bracket here, the ln of the 2x take away 1. Okay. So there we go. There and there. Remember, we're always subtracting there. So upper limit goes in the left one, the 4. Lower limit, the 3, goes in the right one. There. Okay. So if you think you can sort out the contents of both these brackets, 2 times 4, take away 1, that's 8, take away 1 is 7 here. 6 take away 1 is 5. If you think you could do that, so here, sorted that out, then it would be calculator time. You could do that. Fire it in the calculator. That's fine. So maybe come out with that there. And take your time with this stuff. So however many decimal places you want to go to, that's fine. If however you had a course where you dealt with laws of logarithms, what you might know about laws of logarithms, if ln take away ln, that actually becomes a division here. And you're going to get the same answer, regardless. Okay. That's just me giving you a little bit extra there, folks. But if you weren't in that day, you just go there, back to that there, and you'll be fine. Sorry for telling you these things, but there's actually some people who remember this stuff. So it's for their benefit as well. With maths courses, it's not always about lowest common denominator, just giving you limbo, balancing levels. Okay? Sometimes it's good to go a wee bit higher. Okay? Because there's a lot of clever people out there who appreciate this stuff. Okay, that's fine. And Let's see. There's a wee exercise for you. So, this is in the video. So you copy them down, and I'm not giving you the answers. Okay, so you just have a go at them. So I'm going to check how much time that took me there. Oof, that was quite long. So what I'm going to do is I'm going to stop there. That's what I'm going to do. I'm going to stop there.